we're moving into 6.5 today on this lovely Thursday. And I had students try these couple problems on their own. Let's see how we did.
I failed the second one.
As soon as I start breaking up this first one, that's perfect cube. Do I even need to worry about absolute values in my final answer?
No, because it's odd.
Because it's odd. Good.
That's cool.
Now, A is already written as a perfect cube. That's nice.
Uh-huh.
How could I write?
Cube.
How could I write negative 64? What's cubed?
Negative 4.
Negative 4. I think you grade it in. All right. What about y?
Y cubed.
Y cubed would give me y to the 9. All right. So what happens here is the cube root cancels out these cubes. So you should have gotten negative 4y cubed.
I'm a genius.
Raise your hand if you got that right. Air fives.
I know.
Okay.
That was the first.
I heard Riley say 1/16 could be written as 1/2 to the 4th.
1/2 to the
And that is correct because what we know about exponent properties, if I raise a fraction to an exponent, 1 to the 4th would give me 1, 2 to the 4th would give me 16.
Yep.
Or 1/2 times itself 4 times would give me 1/16.
Yep.
Okay.
Don't write it out.
What about the B? Squared. Now I do see even roots. I'm kind of on the lookout for even odd pattern. But once I fourth root those perfect fourth powers, I see on the B I get out an even exponent, so I don't need absolute values. Only if it's even odd. Okay. So basically, this lesson is very similar. So if you feel like pretty confident with these any number roots, that's going to set you up for basically the skills you need to do the problems in lesson 6.5, which is we're going to simplify radical extractions. We're going to
lessons are in chapter 6.
add, subtract, I don't know, multiply and divide. So just as a review, we talked about these properties yesterday. If you have two separate radicals, as long as they have the same index, you can multiply them together. Okay, so like the cube root of 9 times the cube root of 3, we could multiply that together to get the cube root of 27. You can do that. You can multiply any radicals together as long as they have the same index. And you can use this property backwards, which we do a lot when we're simplifying. Where if I have the cube root of 27, I could break it up as 3 and 9, right? We've been doing that like so. Okay, and then we'll kind of get more into the quotient property ones once we do rationalizing ones. But let's do some product property ones first. Okay.
Just like last time.
So this is pretty similar, yeah, but I kind of threw in some ones where there's stuff kind of left over underneath the radicals, okay?
Number 2.
So ones we did in lesson 6.4, they always came out to like perfect cubes or perfect fourth power. So let's take a look at, the difference here between number 1 and number 2. Now, number 1, I could rewrite x to the 6th as a perfect third power.
X squared 6.
X squared to the 3rd. Good. Yep. Do I have to worry about even odd?
No.
Nope. Odd index. That just ends up being x squared. That's basically what we've looked at so far. So what happens if I have something like 17 that's not perfectly divisible by 3?
You split it off.
X to the 16.
Good. We're going to split it up and put it to as many perfect cubes as we can. But I don't want to do 16 because 16 isn't divisible by 3 either.
I was thinking you were 9 and 8. 9 and 8.
15. 15.
What's 15? What?
Right? Couldn't we split this up as x to the 15
So it'd be x to the 5th to the 1st.
15 is 5.
times x squared. So you basically want to think like, what's the largest group of 3 I can do? And here, that would be x to the 5th to the 3rd. So basically, guys, take your power and keep subtracting until you get to something that's divisible by your index. All right, so 17 doesn't go into 3. What about 16? Nope, 15. Yes, bingo. I could rewrite that. So here, these would cancel. And I would get x to the 5th. And then this cube root of x squared would just have to stay behind in the radical because it's not a perfect cube. Okay, I kind of did a couple like that. And you guys have done that with square roots, right? If I'm square rooting 45, that's not a perfect square.
No.
but you break it up into 9, 3 squared, times 5, and we write that as 3 root 5, right?
Yeah.
You keep behind what's not perfect.
That just sounds bad.
Right? Does not sound bad.
What?
What sounds bad?
You keep behind what's not perfect.
Why is this
Okay.
bad?
Now let's take a look at these examples.
Perfect. You ignore it.
No, you don't. You leave it in the radical.
Oh, so it just gets what's left over.
Pretty much.
Like my dog.
It stays inside. Maybe
Wow.
Maybe it wants to stay in there.
Wow.
Maybe it likes to be under the radical and wants to stay in there.
Yeah, it stays out.
Alright, so let's look at the difference between these two.
Very different.
Different. This just cancels, right?
Yeah.
But
Pretty straightforward.
No,
What?
isn't it even? It's even odd.
What?
Oh, even.
Oh.
What?
Whoa.
Oh boy.
Good. Even odd. Nice catch.
Good job, Connor.
Nice job, Connor.
Even odd.
Wow, you're so hot,
Someone
Connor.
pay attention. How could you see that?
Even
You
odd.
probably
Good catch.
can't.
Paper.
Oh.
Paper.
Let me ask you this. Could we do this?
Nope.
No.
Could I split it up subtraction like that?
No.
We're going to 81.
Nope, you cannot. This is a no.
Big naughty.
No what?
You can't split up subtraction like that.
No.
So your answer is just this. That's as
So you
simplified
can
as
only
we can go.
simplify if it's multiple.
Wow, that's wild.
You can, yep, and that's it. That's the big concept here is you can only split it up if it's a product or a quotient, not adding and subtracting. Good.
Quotients? Every
Yeah.
those two?
As you should be.
Why we can't do that?
Yeah.
Because math.
The only time, so let me just give you this example. Let me give you like a number example. Let's say we have, ooh, I'm gonna try to think of one that comes out nice. Let's say we have 5 squared minus 4 squared. Okay,
1 squared.
so that would be 5 squared is 25 minus 16, that'd be 9, and we get 3. Oh shoot, is this gonna work that we cancel it up?
What?
Yeah.
Because we square it and we get 5. No, it won't. Okay, so let's say, so you're thinking like, oh, couldn't I just do this?
You're gonna be 5 minus 4 and be 1. Wouldn't it?
Yeah, and that's not 3. That's not the same as 3, right?
Yeah.
Okay, you can't split this up. So reasoning, I mean, order of operations, if we did have real numbers, we'd have to evaluate the powers first and then do the radicals. And you can't split it up with subtraction like that. Here's a numerical example of like why that doesn't work. We don't get the same answer. And we will get to how you add and subtract radicals towards the end of this lesson. I don't know if we'll get to it today. We might.
Nope.
So basically there's nothing you could do here. Now, did you say like couldn't we factor it? Did you say that?
Not.
Okay. Technically, x to the 4th, you don't have to write this down, minus 81 is a difference of squares. So we could do this. But there's not going to be any perfect 4th powers that come out of this. Like it's not like I have that factor 4 times. So really by factoring it, I'm never going to get something like this, right? So you could like recognize like, oh, maybe I could write it as a perfect 4th power. But in that case, those factors wouldn't break down to the same thing times itself 4 times. And I wouldn't give you one that you have to recognize that. What I want you to recognize is you cannot split it up with adding and subtracting like that. Got it? Who's going to be the first one to do that?
Me.
Wesley.
Oh.
Okay. Let's try another one. I see even, so I'm on the lookout for even, odd. 11's already written as a perfect 6 power.
Sweet.
Nice.
3 to the 6.
Okay, what about x?
Why?
Why?
3. Y, are you saying y is already perfect? You're right. What about z?
Z
squared.
Squared. All right, we're on the lookout for even, odd.
It was 2.
Because there's a lot of evens here.
Where's James?
11, x cubed, y,
That's
z squared.
That's not one.
Which ones need absolute values?
X to Y.
X and y. Good. Okay, so this we know how to do. This is kind of a review over what we just did. What if I have something like this?
You must split.
where, look at my B, I have 13. I'm like, ooh,
Like
13.
12.
Okay, let's see what we can do. First of all, could I write 16 as a perfect fourth power?
2 to the 4th.
2 to the 4th. Okay, that's good. What about 24?
Yeah, it's
6 to the 4th.
8 to the 6 to the 4th. Good. Now we have this dilemma with the B.
Dilemma. So do like B 3 to the 4th and then do like a B.
Okay, Wesley has an idea. He said, let's do B cubed to the 4th, right?
Uh-huh.
There's 12, but I have 13, so I have one B that's left behind. Or B.
Behind.
Yeah. That's funny. Your brother made a really funny joke in class one day. Remind me to tell you that at the end, okay? 2, 8 to the 6. Ooh. You notice for the B here, I have
B to the
even,
4th.
odd.
Oh, we just do that with this?
Even, odd. That still needs absolute values. And then I have that 4 through to B that's just left behind.
Would you ever put absolute values in the radical, like around the radical? Or
Nope. So this is basically the new part of this lesson is like you might have ones now where not everything comes out perfect. Okay, that's basically all the new stuff. But as long as you know how to break up the roots, you can like visualize this pretty easy. And anything that's not a perfect fourth power,
Can we be done for the day?
just carry
No,
out.
Willis.
Nope.
We are never done.
We're
on
gonna
that
keep this
grind.
on 10
We're on
minutes.
that grind set.
We have 9 minutes.
We're on that
All
grind
right.
You have
set,
to tell me a
Willis.
joke, so that's 8.
Now, one thing with radicals, you guys know this with square roots, is that they can never be left in the denominator, right? Like if I have something like this, 2 over the square root of 3, technically somebody somewhere along the lines decided that's not considered simplified and we need to rationalize the denominator. Now what you probably got in the habit of doing and you didn't even know what you were doing is you were making the denominator a perfect square is really what you were doing. By multiplying the top and bottom.
Oh, yeah.
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 Like you knew the rules always like, oh, just take whatever's in your denominator and multiply that on top and bottom. But what you were really doing
Make it a perfect square.
is you were making it like 3 squared so that you would just get 3.
Yeah.
Right? So we can use that idea for other nth roots. So let's try this one. All right, if I have the cube root of the fraction x over 5, my first thing I could do is I could break that up as the cube root of x over the cube root of 5, which would probably be your first step as if these were square roots. Now the issue here is 5 is not a perfect cube. So I have to rationalize my denominator. I can't leave this radical in my denominator. Now here, you might be thinking, couldn't we just multiply the top and bottom by the cube root of 5? Which is not a bad idea, but is that going to give me a perfect cube? Is 5 times 5 is 25 a perfect cube?
No.
No. Any ideas?
Multiply it by something to get a perfect cube.
Okay, what should I multiply by?
Here.
2 for 25.
Okay, 25, because you would have 5 times 5 times 5.
Really?
Or do this. Do you guys agree that that would give me 5 to the 3rd?
Yeah.
See that thinking there? And you can do this as long as you do it on top and bottom.
Oh.
Okay? So watch what happens here. Watch what happens in my denominator. I'm going to get the cube root. I'm not going to write it as 125. I'm going to get the cube root of 5 times 5 squared, which is 5 to the 3rd. So I'm trying to get my denominator to be a perfect 3rd power because this is a cube root. Up top, I would write this as the cube root. I mean, you can do 5 squared, 25x. And then, once you get your denominator perfect cube, those would cancel. And that is rationalized because my denominator would just be 5.
Mine's struggling.
Should you take the 25 out or not?
There's no perfect cubes that go into 25.
Oh, this cube. Duh.
This one's stuck under the radical. So also you can't divide the 25 into 5 because the 25 is underneath the radical and the 5 is not.
Pretty bad.
Sometimes it could come up though. That was a good question, Wesley. Like maybe if I got the cube root of like 48, technically 8, which is a perfect cube, goes into 48. So you might have to keep breaking it down. I don't think that comes up a whole lot, but it's not like off the table. All right, let's try one like this. This is a square root. It's not bad. First step would probably be to square root the top
Square root the top.
and square root the bottom.
Why is that funny?
He just repeats everything I say.
Oh.
I'm like flattered by it. I think you just want to
He
be me.
envies you. He's
Yeah, he's just
inspired.
trying to be me. That's
He
fine.
wants to be
Spider-Man.
Okay. Looking at what I have here, is my bottom going to come out to a perfect square?
Yeah. No.
only if you want it.
7.
We
No.
can make it. We can make it.
How can we make it?
Tell him to.
Yeah, it's a special number.
Ask him
What should we
kindly.
multiply on top and bottom by?
9.
7.
What's going on?
Okay, let's not go like way more than we need to.
I said 7.
2.
I said 7. What should give it to 9?
Who said that? Just X?
Yeah.
Why?
Oh,
make it
yeah.
genius! Oh my!
It's a
That would
perfect
be.
square.
Oh my
well,
God.
We could write it as
Now we have to
4 and then 2.
if I had 8 of these, I
Oh.
could break it up, right? But 7 is not divisible by 2, but 8 is. 8 is. So you now some of you are shouting out other numbers, which you could do it that way, but then you're gonna have to simplify more. So my advice to you would be, try to keep it as small as possible. If I do this up top, I get the square root of x, y to the 8th. We'll simplify this in a second. And on the bottom, I get the square root of x to the 8th. And now I can simplify these. So y to the 8th would be y to the 4th squared. Similarly, x to the 8th would be x to the 4th squared. Everybody with me?
Yes.
Oh, you split
I'm
it
just
up.
now I'm simplifying.
Okay.
Now I'm simplifying. So
Alright.
those cancel.
5 to the 4th square.
So I would have y to the 4th, and then I have that square root of x left up top over x to the 4th.
That's amazing.
Nice
Wow,
job,
that's
everybody.
really
You're really mean right now.
How?
You're being sarcastic. No,
I'm
That's
Can we
do you
be
can we cancel out these x's?
No,
No.
because there's
It's
one
radical.
that's
Radical.
radical.
It's in the garage.
It's in the
I think
garage.
that's a stopping spot.
I agree.
End of the page.
All right. Yeah, the next problem's really long
Gotta
and
tell
intense.
us that
Let's
joke.
go.
Let us pray.
Oh,
So we'll stop there.
early.
Gotta tell us that joke.
Yeah, I gotta say this joke that Matthew said really funny.
I hope it's really funny. What was that?
Matthew might have told me because he